Hi, welcome to me313 Mechanical Engineering Thermodynamics. The topic of today is the Rankine reheat cycle, and the sections in the textbook are 10.4 to 10.5. So here are the three learning outcomes. At the end of this, you'll understand three cycle modifications that we can make to the Rankine cycle that will increase the thermal efficiency from the basic cycle. You'll know that there are three external limits as well to these modifications. For example, material limits, as we'll see in a moment. And then finally, you'll be able to solve an ideal Rankine reheat cycle for the thermal efficiency. All right, so let's look at the traditional Rankine cycle. I've got an ideal Rankine cycle here. So we have this point right over here, which is the condenser outlet we traditionally call point 1. We go through a pump up to point 2 right there, and then we heat all the way up to this, which would be point 3, and then this is our turbine down to point 4. So that's the kind of traditional Rankine cycle. I've got vertical lines on the TS diagram, being that this is an isentropic pump in a turbine. And so we'll go ahead and just stick with those for now. There's a couple things we can do if we want to increase efficiency, and keeping in mind that efficiency is the net work over the heat that I put in. So effectively, what I want to do is I want to increase the net work, which is increase the area inside this green curve. There's a couple ways I can do it. Think about it. You're just trying to expand this curve. So one thing I could do is I could go ahead and just drop this down to some lower pressure, for example, that point right there. And so you can see that clearly the area of this would be much larger, and it turns out you would have a larger efficiency. And one of the things to note is that the temperature and the pressure along this line down here are tied. That's the saturation temperature and pressure. So if I want to lower what the condenser pressure is, what I need to lower is that temperature. And if you remember from our last video, the temperature here in the condenser is controlled by our cooling water. So there's sort of a limit to how low I can go on here, because it's going to be controlled by my cooling water temperature. And there's another danger I run into, which you can see as I've drawn here, is that what I have here is my turbine outlet is a mixture, which means I've got some liquid and some vapor. And so this is actually not a very good thing to happen, because when you have liquids and vapors together in equilibrium, you can get corrosion. And what you see here are some turbine blades that have become corroded and pitted, and the reason for that is because of two-phase flow inside the turbine. There are ways to address this, but traditionally that is a problem, and you want to stay out of the two-phase region at the outlet. Now, another way we could go ahead and increase the efficiency is we can go ahead and just increase the high temperature. So this right over here, this point is T high. And what I could do is just go ahead and keep heating it and keep heating it and keep heating it, so that I could go ahead and increase the area that way. And so that would clearly have a larger network area. The heat that I'm putting in here is going to be balanced by the amount of work that I get out, so I have an increase in efficiency. But there's clearly going to be a limit here how hot I can get. I'm going to be limited by my material properties, and if I got too hot, I would just start to melt my turbine blade. So there's a limit to how high the temperature can be. Now, there's another thing I can do. Again, if I'm trying to increase the area of this curve, I could go to a higher pressure. So maybe instead of pumping to this point here, I'm going to pump up to a higher pressure, and this would give me a larger area. If again I'm limited by maybe a material property there, I'm going to lose some work here and gain some work here. And so it turns out usually there is some increase in efficiency with higher pressure. It's a smaller trade-off there. It comes at a slower rate than some of these other ones. And there's also going to be a limit to how high I can do it, because if I'm operating at too high of a pressure, I can just go ahead and have my boiler blow up. And you can go onto the web and find all sorts of interesting pictures of boilers that have exploded. And here's a picture of one here. So those are three ways to do it, but they've got what I call our external limits to how much you can go ahead and increase the efficiency. So another way we can do it, and it's a little bit more practical, is called the Rankine reheat cycle. And so effectively what I'm doing, and I have it shown here in the diagram, is I'm taking my turbine from the single cycle and putting it into a high pressure turbine and a low pressure turbine. And so my fluid will go through the high pressure turbine, and then I remove it at an intermediate pressure, and I go ahead and I run it back through my boiler and increase the temperature again, and then I run it through my low pressure turbine. So going from P high at the inlet there, this is coming down at P low, and there's going to be some P medium pressure right there. And so if I look at my TS diagram right here, let's go ahead and draw this new cycle. And so to help do this, I'm going to go ahead and kind of dash in some isobar. So this is the isobar of P high. This is the isobar of P low. And then there's an intermediate isobar. I'll just sketch it in right there. Okay? And so each one of those, and this is some intermediate pressure. So what I'm doing is this is 0.3 is at that point right there. And then I'm going to run through to an intermediate pressure. So instead of going all the way to P low, I'm just going to come to this pressure right there, which is my intermediate pressure, and that's going to be 0.4. And then I'm going to run back through the boiler. And so assuming there's not really many pressure drops at this, I'm going to go ahead and be following that isobar up to, well, I could get as hot as my temperature at T3 if it was a perfect reheater. And so perhaps I go to that point there. This would become 0.5. And then I'm going to go ahead and drop down to this isobar at that point, and then go ahead and condense down back to 0.1. And so you effectively see here's my increase in area. I'm going to have an increase in net work by reheating it, and I'm going to have a little bit of increase in input because I've got a reheat there and I've got a Q in there. But it turns out, as we'll see here in just a moment, I do get an increase in efficiency by reheating. A couple of things. Note that I said that T5 here was the same as what I have up here at T3. Okay, that means that I've got an ideal reheater. Clearly, the temperature T5 might be something lower, but it would have to be specified in terms of how efficient this is. Normally, they're fairly efficient, and so the assumption that the temperature and the reheater are the same is a pretty good assumption. Okay, so let's go ahead and solve an example problem. Here's the example problem I've got. I've got a Rankine cycle, and I have it seams entering at 350 and 10 megapascals. And so it's entering up at some 0.3. I'll put it right up there. That's at 0.3. And it reheats at 2 megapascals. So I've got a high pressure 10 megapascals, reheater at 2 megapascals, condenser at 75. So the way I'm going to do this is I'm going to go ahead and draw up 3 isobars. There's my 10 megapascal line. I'm going to have a 75 kPa line, and then I've got my intermediate one. I'll just dash it in just to make it kind of clear. That's at 2 megapascals. Okay. So those are my 3 isobars. So if I look at my system here, I'm going to start off with my condenser outlet, which will be 0.1. I'm going to pump up to the high pressure, which will be 0.2. I go all the way to the high pressure. I don't stop at the middle one. Then I go up to 0.3 in my boiler. Drop down, if we assume that it's isentropic, which we'll do for now, I'm going to go to 0.4 at the middle. We're going to go ahead and reheat up to 0.5, drop down to 0.6, and then go ahead and run through my condenser. So there's the way my cycle looks. A couple things to note. I'm said that T3 is equal to T5. It's assuming an ideal reheater. And then I've got these isobars. So like the pressure at 2 is the same as the pressure at 3. Pressure at 4 is the same as at 5, and the pressure at 6 is the same as the pressure at 1. Okay? So there's kind of qualitatively I'm going to solve it. Now let's go ahead and solve this. And since we're dealing with steam, which is water, and it's non-ideal, it's easiest to do this in EES. So I'm going to go ahead and move over to EES now to solve this problem. So here we have it in EES, and so let me just kind of point out a few things that I have. Here up front, I've got my specifications. My pressure at 10,000, I have my unit system in kPa, so that's what P3 is. My temperature, high temperature was 350 degrees. Here's my medium pressure, which was P4 at 2,000, and my condenser pressure at P6. So that was specified in the problem. I'm assuming it's a perfect reheater here. I'm not told otherwise, so I'm saying T5 is the same as T3, so there's my perfect reheater. And then I've got those isobaric steps I mapped. So P1 was 6, that's the condenser. 2 is to 3, that's in the boiler. 4 to 5, and that's in the reheater. Okay? And then one last thing I'll specify is a condenser outlet, which is X equals 1. Or sorry, X1 is equal to 0. That means that it's a saturated liquid. Right? So let's go ahead and if we just go ahead and solve this to see what we have here, I just want to kind of point out things. So here are my 6 states. I've got pressures specified at all. So I have one intensive variable there. And I have another second intensive variable at 0.1, 3, and 5. And so what remains is I need to get a second intensive variable at 2, 4, and 6. And once I have any intensive variable there that's independent of pressure, I can go ahead and completely specify the problem. And I can actually do that because going 1 to 2 was the pump. That's isentropic. That'll be my step there. 3 to 4 is the high pressure turbine. If that's isentropic, that'll be my step there. Same thing, 5 to 6, that's my low pressure turbine. let's go ahead and look at how we make that modification. Okay, next when I close that, I reopened it here. So this is where we're at point. And so now what I'm going to do is add those isentropic steps. So I'm going to do that right over here. I've got this stuff sort of commented out at this point, so I'm just going to slowly remove some of these comments. And so here I'm going to be specifying what my entropies are. And so what you can see in these 3 blue lines I just added is I'm just specifying what the entropy is at 1, 3, and 5. All right? And if I go ahead and do that, and now look at my solution table, right? Okay, I see I've got these entropies, and now I'm going to say that S1 was 2 in the pump. So I'm just going to essentially be copying that line down. So let's go ahead and do that. Oops, keep hitting the wrong window there. Alrighty. So now let's go ahead and do those isentropic steps. Alrighty. So here are my isentropic steps that I'm adding. And so what I'm saying simply is S1 is 2, 3 is 4, and 4 is 5. So if we go ahead and look at what we've got now, see I've got my entropy at every point, just copied down, and my pressures at every point. So more or less now I have 2 intensive variables. My problem's completely solved. We can go ahead and solve for all of our enthalpies so we can get our heat inputs and outputs and work. And we've got P and S at every point, so we can go ahead and use that pair. So that's what we'll do on our last little step here. So down here, I'll go ahead and remove this last set of comments. And so what you see I have is I'm using the duplicate statement because I'm finding the enthalpy at P and S for all 6 points, just kind of in terms of efficiency there of writing it. And now I've got my QN step. Now notice there's 2 parts to QN, 3 to 2 and 4 to 5. If we return to our diagram here, oops, that's not my presentation. There we go. We have heat input from 2 to 3, and we also have heat input from 4 to 5. So we need to add both of those. So, that's why I have for QM 3 minus 2 and then 4 to 5. Q out is just 6 minus 1 still. That's in my condenser. And then I have my efficiency of 1 minus Q out over Q in. So go ahead and solve that. And look at my array table here, all of my enthalpy values. They're actually in joules instead of kilojoules. We can go ahead and change that really quickly. So then we got all of our enthalpy values, and then going back and looking at what our efficiency is. Here's our efficiency. We see our efficiency is 31%. Well, there's next thing I want to mention is this problem specified what my reheater pressure was. It had it at 2 megapascals, and you might wonder what's the ideal intermediate pressure. And Brayton cycles, we were able to determine it was the geometric root of the high and the low. That's not true of Rankine cycles since we have non-ideal gases. So you might really wonder what is that ideal pressure, and there's no easy equation for it, but we can have EES find it for us. So that's one other kind of interesting thing I'm going to do here. So you go under calculate, there's this min-max, and it's going to let you minimize or maximize our function. Now first you've got to have a degree of freedom. You've got to vary something, and what we want to vary is this intermediate pressure P4. So I'm going to go ahead and comment out P4. That's my middle pressure. That's the reheater pressure. And now if I go up there, the min-max, okay, it's going to let me do it. And what I want to do is I want to maximize. I'll choose that radio button, the efficiency. And then what do I want to vary? I want to change P4. All right, so that's what we're going to go ahead and maximize it. And it wants me to set upper and lower bounds on it. So I'll go ahead and do that. Well, we know P4 has got to be, I don't know, at least 100 kPa, and it's not going to be more than, I'll say 9,900. So that's because the highest pressure was 10,000 and the condenser was at 100. So those seem like a good set of bounds. So if I go ahead and do this, it optimizes it for me. I found that the efficiency I could get as high as 32.22%, and that would occur at a P4 of 5782. So clearly, 5782 would have been the ideal intermediate pressure to have. So here we have it. Problem, they solved it, 5782. These are all of my other values, and my maximum efficiency is 32.22. Okay, I think that might be it. Let's see what our next slide is.